Dear learners, my name is Dr. Subhasiddhas. I am working as an associate professor in the Department of Electronics and Communication Engineering, SR University, Telangana, India. So this is my YouTube channel where I will post the videos about the different basic working principles and functions of analog electronics and other devices and circuits. Please do like, share and subscribe my channel. So today's topic of discussion is laser. So what we are going to discuss here, as you might be already aware of laser or what is the function of laser, but here what we are going to discuss about the construction of the physical structure of the laser, the working principle of laser, and how the PN junction diode lasers work for the regular applications, the characteristics of laser, and so on. Okay, let's start. So, laser is the light amplification by stimulated emission of radiation. Okay, so the here comes the full form laser light amplification, light amplification by stimulated emission of radiation. Okay, this makes it laser laser. Okay, so a laser diode is a semiconductor diode that transmits coherent and highly focused light through a process called stimulated emission. Okay, let's try to understand coherent and highly focused. Okay, so that means when the lights are emitting, let's say from this diode, so this is the circuit symbol of that laser diode. Let's say the lights are emitting like this. Okay, so if the lights are emitting parallel in a focused way and it is also coherent, that means the same phase going like this, it is emitting, then it becomes laser. Okay, and the action or the threshold above which this kind of actions are seen, that is called the lasing action. But what if instead of getting like this, what if the light emits like this way, like in a scatter manner? So although the diode is emitting the light, but still it will make it to laser because the basic condition for a lasing action that the light emission should be coherent and highly focused. Okay, and the process by which we are getting this kind of light emission is called the stimulated emission. Okay, stimulated emission. We will see later part of this video that stimulated emission is one type of emission where it was forced by some light or some external excitation that the diode should emit the photons, or if it is in the visible way, then it will become light. Okay, so but there will be some devices where the spontaneous emission also happens. So we will see those things, that spontaneous and stimulated emission both are possible. Okay, we'll this see this thing later. Okay, now we'll see what is semiconductor laser diode. Okay, so we will see what is semiconductor laser diode, right? Because why this is specific, why we are saying semiconductor laser diode, because this laser can be from different, like gas laser also available or some other power also available. So this is very much specific that we will focus our discussion on the semiconductor laser diode. Okay, so it is specifically fabricated PN junction diode. Okay, this is specifically fabricated PN junction diode, and this diode emits laser light when it is forward biased. Okay, so laser light does not like uh, vary from the LED. The only difference is that the light emission is coherent and focused. Okay, so the laser diodes are known as semiconductor lasers. Okay, junction lasers, junction diode lasers, or injection lasers, because here the carrier injection also happens. So these quite a few names we can give it to these semiconductor laser diodes. Okay, so any name is fine. Okay, okay, let's move to the construction of the laser diode. Right. So here is the physical layer construction of the diode. Okay. So let's first try to understand what is written here. It is saying that semiconductors gallium arsenide, like gallium arsenide, indium gallium arsenide, are used to build a laser. So here it gives only few of the examples, but it is not necessary that always it will be like that. Okay, it could be from different materials as well. Okay, it could be indium phosphide based laser or some other alloy, any other ternary alloy, any other ternary alloy of compound semiconductor, compound semiconductor. Okay, so only few of them are mentioned here just for illustration purpose. Okay, so we will see that it comprises of few layers. What are the layers? We will see those things now. Okay, here this is the laser diode construction. So the bottom layer is N-type material. Okay, and the middle layer is intrinsic layer, and the top layer is P-type material. Okay, so here as you may be aware that N-type material. N-type means what? N-type means it is electrons only. Okay, electrons is the majority, and here the p-type materials means hole is the majority charge carriers. Hole is the majority charge carriers. Okay, so electrons and holes are the majority charge carriers from this. Okay, here intrinsic layer means no doping. Okay, no doping has been done here, right? That is why it is called the intrinsic layer. Okay, so this is the layer structures of the semiconductor laser diode. As you can see, the metal contacts are coming into it, and on the back bottom also the similar kind of metal contacts are there. Okay, so this is basically the structure of the laser diode, right? And as you can see, this is for illustration purpose. It is not exactly the same place the laser is coming out. So it is just showing that at the junction, whenever the lasing action happens, we will see the laser output comes out from here. Okay, let's say it is coming in this direction. So all the lasers will be coming in this direction. Okay, so it will be coming in this direction. So that's why it will be called the laser. If it goes like this, goes like this, goes like this in the different directions, it will not give the lasing action. Okay, we'll show you next. Okay, so now we'll come to the working of laser diode, right? So when a PN junction diode is forward biased, please remember this thing. When a PN junction diode is forward biased, the electrons from N region and the holes from the P region cross the junction, and recombine with each other. This is very common. We know from our basic understanding of PN junction diode that whenever the diode is forward bias, obviously the electrons from N region will try to go to the P side and holes from the P region will try to go to the N side. And when they will go to the other side, they will be recombining each other. Like these things will start and this process will go. Okay. So during the recombination process, okay, so during the recombination process, the light radiation, that is photons, we are saying that light radiation is photon, is released from a certain specific direct bandwidth semiconductors like gallium arsenide. This icon should not be there. So this should be gallium arsenide, right? So this light radiation is known as a recombination radiation. Okay. So let's try to understand if this is your valence band and this is your conduction band, and when this comes like this, it gives us the value of Ag. But this is for the case of direct bandwidth, and this process is called the recombination. Okay, because the electron jumps from here to here and recombine, the holes are here, electrons are there, so it will recombine, right? So these things will happen and the process we will call it as the recombination radiation. Okay, now we will see some specific things. Okay, how that thing will happen? A laser emits a beam of electromagnetic nature which is coherent in nature. The working of the laser diode is based on, okay, let's try to understand. The laser emits a beam of electromagnetic nature which is coherent. This is the electromagnetic wave which is coherent in nature. Okay, so the working will depend on the three different processes. We will try to see all those things. So basically, it is just emitting H okay, whether it is coherent in nature, that will depend, and based on that we will categorize those some. So first thing comes as the absorption. Okay. The absorption means the electrons jump to a higher energy level by absorbing the energy when a certain voltage is applied. Okay, let's try to understand what is happening here. The electrons jump to a higher energy level. Higher energy level. Okay. So electron has different energy levels. It can stay in different energy level. Those are called the different states. By absorbing the energy when the certain voltage is, so energy absorbed. Okay. From where the energy is coming, voltage is applied here. Okay, so the voltage is applied, and from the voltage it is taking the energies, which is the electrical energy, by the way. So this process is called the absorption. Okay, so absorption happens when electrons going to the higher state. Okay, so now this absorption process is complete. Then what happens? We'll see spontaneous emission. Okay, we'll see these 2 points: spontaneous emission and stimulated emission, and we'll try to categorize the emissions into these two. Okay. So when electrons in an excited state return to a lower energy level, okay, excited state return to a lower energy level on their own. So this is the main factor, on their own. Okay. For the emission, anyway, electrons are coming from the higher to the lower state, but how they are coming? Are they coming by their own, or they are forced to come? And depending on that, we will categorize these two types of emissions. Okay. So when the electrons in an excited state return to a lower energy level on their own, the emitting photons, okay, the emitting photons of energy equal to the energy difference between the levels. Okay, right? Understood? If it is going, suppose here it is showing that it is going from N to N. Okay, so the energy of emission will be EA minus EN. So this will be the energy of emission. Okay, that means it will give rise to a emission energy of an emission energy which is equal to the difference between the two. Okay. So anyway, so the main thing here to remember is that they are going by their own wish. Okay, we are not forcing them to go. That means it is spontaneous in nature. Okay, so that's why this type of emission is called spontaneous emission. Okay, now it comes that okay, if they are not going by their own, can we force them to go? Yes, we can do. And that type of emission we will call them as the stimulated emission, right? When an electron excited by a photon recombines with a hole and emits an additional photon identical to the incident one. So here are two things. When an electron excited by the photon, okay, so electron excited by the photon recombines with a hole, recombines, okay, recombines with a hole and emits an additional photon, okay. That you see, one H nu is coming, right? One H nu is coming, and when recombine, it gives rise to extra photon. So that is the additional photon, which is identical to the incident one. Okay. So what is the process here? An electron which is excited with photon, and this electron recombines with a hole and emits an additional photon which is obviously identical to the incident one. Okay, so that is how this stimulated emission happens. Okay, I hope you understood all these spontaneous and stimulated emission processes. Okay, okay, now we'll move forward to understand the p-n junction diode laser. Okay, so at zero bias, the Fermi level. Okay, right side, you can see the band diagrams of p-n junction diode, and as we know, this is the junction. This is the junction as per our previous one is concerned. So we'll see three different conditions. First one is zero bias, that is no bias, and second one we'll see the forward bias case, and third one we'll see that more bias. Okay, now let's try to understand one by one. Okay, so at zero bias means no battery connected, there is no biasing happening. The Fermi level EF remains uniform. The Fermi level, okay, you see here, the Fermi level remains uniform and equal on both sides of the junction. You see, if you see this line, you see that clearly uniform and equal for both the lines. Okay. So this is a must know fact that you should always remember that whenever the equilibrium is established and there is no bias connected to the p-n junction, the Fermi level throughout the device will be same. That means it will be equal on both sides of the junction, right? So this is one condition at the zero bias or no bias. Okay. Now we will see what happens if we bias them. So here, when a forward bias voltage VF, okay, forward bias voltage when a forward bias voltage VF when a forward bias voltage VF is applied, right? Forward bias voltage VF. So VF is the energy we are putting, and you can see the P side energy level shift downwards. P side energy level shift downwards, right? Relative to the N side, making the Fermi level difference between both sides equal to EV. Okay, EV amount of Fermi level difference happens, and as we can see from here, the EF is the voltage and the amount of energy is just EV. So EV amount of energy has been put in the inside region so that the Fermi level of the inside goes up by this amount, or in other words you can say the Fermi level of P side goes down by this amount. Okay, so now you can see that this amount, this region is the Fermi level region. Earlier it was very much lower. Okay, so this is the condition when you apply Fermi level. Now what happens if at higher applied voltage? So that means what we understood from the second condition from the figure B, that if we apply forward bias, this band bending will be reduced, or the Fermi level in the N side will go up so that it will be band bending will be less. Okay, and if we keep on increasing the voltage, it will become almost straight. The Fermi level will go up and up again in the N side, so that the band bending will almost be gone. Okay, because it is almost parallel. Okay, so the electrons from N side fill the conduction band. Okay, fill the conduction band in the junction region, while holes from the P side occupy the valence band. Okay, in the image also you can easily see that it is almost filled. Okay, now we'll see how we can control it. Right. So the minimum frequency nu, so this is frequency nu. Okay, so this should be frequency nu, right, of the photons emitted in the band-to-band transition is given by nu is equal to E by H. Everybody knows this formula already. Eg is equal to H into nu. So that means the nu is the frequency, which should be equal to the band gap energy divided by the Planck's constant H. So this is for sure. We already know this formula. Now we will see some conditions. The maximum value of nu is given by EFN minus EFP greater than H. What is this EFN and EFP? So this EF stands for Fermi level and N stands for N side. So the EFN stands for Fermi level in the N side and EFP stands for Fermi level in the P side. So the Fermi level, so the difference between the Fermi level of N side and P side should be greater than is equal to H nu. Okay, H should be greater than is equal to H nu, which is again equals to the band gap. Okay, and the operating condition of a PN junction laser diode is EFN minus EFP greater than equal to H nu, which is greater than equal to H. This condition already we discussed. Okay, now we have learned about all these things, that what is the condition for the PN junction diode laser lasing to happen. Okay, now we will see the characteristics. Okay, So the threshold voltage, we'll see what is threshold voltage, right? What is threshold voltage? This is because emissions are weaker at the lower energy. Okay. You might be thinking that if we give smaller energy also, the emission will happen. So that is not going to happen. So this is because emissions are weaker at the lower energy. Okay. So this is the threshold voltage after which the emissions become so high that it is become very significant. Okay. So in the image also you can see this is the threshold voltage. Actually, if you see up to the threshold voltage, the emission is dominated by the spontaneous emission. But after the threshold, actually the stimulated emission also start working, and we can see huge amount of emission for that. Okay. Now the laser action begins when the diode current exceeds the threshold. Okay. From here, actually, we call this resonance. Okay. Resonance starts. Up to this, we cannot say the resonance starts, making optical gain equal to system losses. Okay. So this is the resonance which begins when the diode current exceeds the threshold. Okay. So this is what we understood from the power versus current curve also. Okay. Now we'll see characteristics of laser diode again with respect to power versus frequency. Okay. So you see this graph, we are going to explain it. When the current is below the threshold IT, okay, in the last slide we have already noticed below the threshold IT is very less. The emitted light is weak and results from spontaneous emission similar to the LED. These things we already know that before the threshold, lasing action does not start. And because of this, the light emitted is weak, and obviously it is from the spontaneous emission, so obviously the emission uh, capability is less because of the spontaneous emission, and we are having a weak emission which is similar to the LED. So the basic difference here is that in the laser the lasing action happens. Because of this lasing, it is different from the LED. Otherwise, LED also emit light and laser also emit light. So there is the difference that for the laser it is focused and coherent beams. Okay. Now the second condition comes if I greater than IT, the radiation becomes much more intense and with a spectrum confined to a narrow band of frequencies. You can see this thing. This is so much narrow. This is why it is called lasing action. And the diode laser operates with various longitudinal modes with frequencies within the range of the radio. Okay. So it has various frequencies. So we can see the lasing action or this kind of peaks at different harmony. Okay, first order, second order. You can see these things. Okay, as per the frequency is concerned. Right. Now we'll see some applications just to understand that whether it is worth understanding the working principle or even it is worth to know about the network. Okay. So the first application is it is widely used in optical fiber communication. So nowadays, as you know, the optical fiber communication is everywhere, and for that communication system, laser diode is used. Okay, it is used to heal the wounds by infrared radiation. Okay, it is useful in the medical science also. In the human body, the wounds could be healed by infrared radiation. It is also used as a painkiller, right? It is used in laser printers and CD writing and reading. You may be already aware of this thing, CD writing and reading. Maybe nowadays nobody is using CD, but still the method And laser printers are there nowadays. Nobody is using that inkjet lasers, sorry, inkjet printers. So the laser printers are also useful, and they are also we are using the lasers. Okay. So what are the key understanding from this video? That laser diode construction and working way, we understood that how the lasers are working, and we saw the characteristics of the laser diode as well from that cards. Okay. So what could be the question coming from here? So the question could be like this: what is a laser diode, and explain the working principle. Describe what happens when the current is below and above the threshold point. Okay. So basically you have to understand the working principle along with current characteristics. Okay. Okay, I hope all of you have understood the basics of laser diode and how it works and what are the characteristics of it. Okay, see you in the next video. Thank you for watching.